G P over P times norm of F in L1. So this is norm of F L1, and I have 1 plus P over Q times norm of G P over P. And if so, this implies that norm of F star G over P is less or equal. Now 1 plus P over Q, this is equal to P, because we have 1 plus P plus 1 over Q is 1. So 1 plus P over Q, this is equal to P. So I have norm of F in L1 and I have norm of G in L2. And so we have, if F is in L1 and G is in LP, then the convolution product is in LP, and the norm of the convolution product is less than the product of these two norms. And so we prove this for general P. And this result is very useful because you use it to make some estimation. Anytime you have to compute to estimate the norm of the convolution product, we can use this result. If we know that one is in L1 and the other one is in LP, then the convolution product is in LP. And we have this estimation. We have a more general result of this. So this is the general general Young inequality. The general Young inequality says the following thing: if you have let P, Q, and R between 1 and plus infinity, if such that we have 1 over P plus 1 over Q is equal to 1 plus 1 over R. If F is in LP and G is in LQ, then the convolution product F star G is in LR, and the norm of F star G in LR is less than the norm of F in LP times the norm of G in LP. Look at, if for example, if Q is the conjugate of P, so it means that 1 over P plus 1 over Q is 1. So it means that 1 over R is equal to what? 0. To 0. So it means that R is equal to what? Infinity. R is equal to plus infinity. So if F is in LP and G is in LQ and P and Q are conjugate, then the convolution product is in L infinity. Is in L infinity. We can see all these cases. For example, here if you take P to be 1, if I take P to be 1, if P is 1, so I have 1 plus 1 over Q is equal to 1 plus 1 over R. So we have Q is equal to R. And this we have seen, because if F is in L1 and G is in LQ, we have seen that the convolution product is where? Is in LQ. Here we have Q is equal to R. So this is the general Young inequality. So for convolution product, if 1 over P plus 1 over Q, it means we can, if for example you have F is in L3 and G is in L4. Let us see. So we will have 1 over 3 plus what? Plus 1 over 4. This is equal to what? This is equal to what? This is 7 over 12. And this we cannot write like this.
It's less than 1.
Huh?
It's less than 1.
This is less than 1. This we cannot write like, we cannot write in this way. So, because I want you to know if f is in L3 and g is in L4, where is f star? Where is f star g? Where is f star g?
So it means that in the general inequality, the sum 1 over p plus 1 over q
Will be bigger than 1. Will be bigger than 1. Otherwise it doesn't work. Okay. So this is, now let us see how to use convolution product to make smooth function or to approximate a measurable function by a smooth function. So first we define modifier, and for this we take let phi any L1 function in Rn such that the integral over Rn of phi dx is 1. We take arbitrary function phi in L1 such that the integral is 1. And for epsilon positive, let phi epsilon of x defined by 1 over epsilon power n phi of x over epsilon. I fix phi arbitrary, and for each epsilon positive I define this new function phi epsilon. Here we can see that each phi epsilon is a function in L1 of Rn, and 2 we have also the integral over Rn of phi epsilon dx is equal to 1 because of this. We take this just to make this integral equal to 1. So this family phi epsilon, where epsilon positive is a modifier with kernel phi. So anytime you fix phi, you can define a modifier phi epsilon like this. Phi epsilon of x is 1 over epsilon and phi of x epsilon. Each phi epsilon is a function in L1, and the integral of phi epsilon also is equal to 1. So this is the first thing you need.
What do you mean by you can phi? What do you mean by you can phi?
Modifier.
Modifier this kernel.
Kernel.
This kernel. This kernel phi. Phi is the kernel because we get all phi epsilon by using phi. So phi epsilon is defined like this. So anytime you fix your kernel, you get a new modifier. If you want a continuous modifier, so you have to choose phi to be continuous. If you want a smooth modifier, you have to choose phi to be smooth. And you will see, if I want to approximate L1 function by a continuous function, so I need only to pick a continuous modifier, because we will see that from this phi epsilon we can construct a sequence of continuous function if I assume that phi is continuous. Or if I take a smooth modifier, so from this smooth modifier I will construct a sequence of smooth function. But it is not enough. I need a smooth function which converges to the initial function. So this is what
So the modifier is the one you call a kernel.
is.
The modifier chosen is the one you call a kernel. It's just a name.
Yes, it's just a name. It's just a modifier of this kernel phi. This is just a name. If phi is fixed, this family of function is what we call modifier. And for this modifier, the kernel is phi. It means we get all this function by using phi. Okay? And this phi in L1 is arbitrary. So anytime we choose a phi, you have a new modifier. And it depends now what you want to choose your kernel. Okay. So we define modifier, and if I take now, let function f is a function in LP of Rn, or let us take f a function from Rn to R, and I take a vector in Rn. So we denote by TAF a function defined from Rn to R by TAF of x is just f of x minus a. So TAF is the translation of f by a. A is fixed, f is fixed, and I define this new function TAF. TAF of x is f of x minus a. Since now, you will see, since Lebesgue measure is invariant under translation, if this function f is in LP, then TAF also is a function in LP. And the norm of f is the same as the norm of TA. So if f belongs to LP, then TAF also belongs to LP for all A, and the norm of TAF in LP is the same as the norm of f in LP. Okay, so from this, let us see now the first approximate we have. So we take let phi epsilon, a modifier, this kernel phi. Here we assume at least phi is an integrable function, and the integral of phi is 1. And in some case, if we need phi smooth, we will precise. But if I take like this, it means that phi is in L1 and the integral of phi is equal to 1.
Excuse me. The moment you write that, it means that phi is defined the other way you wrote it. That for any epsilon.
Phi epsilon, yes. Phi is fixed, and phi epsilon is defined. Yes. Phi epsilon of x is 1 over epsilon power n phi of x. Anytime I say let phi epsilon be a modifier, we know how to define phi epsilon. Okay? Let p between 1 and plus infinity, and let f be a function in LP of Rn. Then we have the norm of f star phi epsilon minus f in LP. This makes sense because we know that phi epsilon is in L1 and f is in LP. So the convolution product is where? Is in LP. F is in LP, so this is a function in LP. And so this norm is less or equal to the integral over Rn of norm of tau epsilon y f minus f over p dy. Tau epsilon y is just, we know, tau a f. So it means that in this case, our a is equal to epsilon times y. F minus f norm p dy. F is in LP. F is in LP. So tau epsilon y f, this is a function also in LP. So the difference is a function in LP, and so this makes sense. So this norm is less than this norm.
For this course, your tau will always be defined like that in terms of f.
Yes. you can see tau epsilon y f. This is a function, but apply to x, it will give you what? This is f of x minus epsilon y is this. Okay? This inequality we will use a lot. And we can see how to, excuse me, it's here we have, excuse me, here we have absolute value of phi of y dy. It reminds this term, huh? This term. So how to get this? So we can, since the integral over Rn of phi dy is equal to 1, because phi is the L1 function and the integral is equal to 1. So I can write first this term. So I have f star phi epsilon of x minus f of x. This by definition, this is the integral over Rn. I have f of x minus y phi epsilon of y dy minus this integral over Rn. Now I take f of x phi of y dy. Because this is a constant, I integrate over y. So this I can bring out. If I bring out, it remains the integral of phi, which is 1. So this term is exactly f of x. Now if I make change of variable here, because phi epsilon of y is phi of y over epsilon, and I have 1 over epsilon power n. So
could you go through this step because I forgot to follow it.
okay, which one?
How you
This is just, this term is this term. I use the definition of convolution.
yes.
This term is exactly this term. This is the definition of f star phi epsilon.
Okay. Now it's
And this term is exactly this one, because you can bring f of x out, and it remains the integral of phi, which is 1, and you get exactly this one.
it's not.
Okay? So, this is the integral over Rn. If I make change of variable, because here this phi epsilon of y, this is 1 over epsilon n phi of y over epsilon. If I take z to be y over epsilon, so I have y is equal to epsilon z. And I have dy is epsilon power n dz. And so if I replace here, so this becomes only f of x minus, I call again this variable z, I call again y. So it becomes x minus epsilon y, and here I have phi of y. Now I have phi of y, here I have phi of y, so I write in one integral. So all this becomes minus f of x times phi of y dy. This is what we get. And this is, I can write by using tau. So this is the integral over Rn, and this becomes what? Tau epsilon y f of x minus f of x times phi of y dy. This is what we have. So this term is nothing else than this one. Now you have in the note the Minkowski inequality. Minkowski inequality, you have if f is a function defined from x cross y to r. where x and y are two sigma finite measure space. So, and we take p between 1 and plus infinity. Minkowski inequality says the following things. I can remove this. Minkowski inequality says the following things. The integral over Rn of this, so that we have is the integral over x of absolute value, this integral over y of f of x y, here dy power p, this is power p dx 1 over p. If you see, this is nothing else than the norm of the integral over y of f of what? X. So this is the function of x, and so I have y is this dy, the norm p. So it means this is the function of x, because if this is the function of x, so I can even this is the function of x. If I compute is norm, this is less than the integral of the norm. So it means this is less than the integral over y of the norm. The norm now becomes the integral over x, absolute value of f of x, y, and here we have dx power p, 1 power p dy. So if you see, this is, I take this is the integral, this is the integral, the norm of the integral is here, and I compute the norm of the integral. This is less than the integral over y of the norm, but norm of what? Here I take the integral of over y is here, and this term is what? This is the norm of its function. This is the norm of f of, so x is fixed, y, I take this norm p, and here I have dx. So this norm I compute in the space capital X. This is the norm p of this function, but this function is the function of x.
With respect to y.
Yes, here is respect to y. I integrate over y, but this norm I compute over x. And so this is the general, this is the Minkowski inequality. But this inequality says, if this integral is finite, because this integral is always defined, this term, I can always compute this, because I integrate first a positive function. So this makes sense. Even it is equal to plus infinity, it makes sense. But this is not well defined. Maybe because I integrate this function first, and I don't know if this function is integral or not. So Minkowski says, if this integral exists, then this one exists, and this inequality is true. So before we use this inequality, we first need to estimate this term. And if this term is finite, then this inequality is true. So before we use this inequality, first we estimate this term. If this is a finite term, then this term also is finite, and the inequality is true. So if now we have this Minkowski inequality, so this is only what we will use here. Because look at this term is f, we compute, this is f star of x minus f of x. This is what we get here. Now I want to evaluate the norm of f star, f f star phi epsilon minus f in LP. So if I use Minkowski inequality, what is Minkowski inequality here? Minkowski inequality says if I take the norm of this, so norm of f star phi epsilon minus f p, so this is the norm of this integral. This is the norm of this integral. And Minkowski says this is less than what? This is less than the integral of the norm. So this is less than the integral over Rn of the norm in LP of this function.
But excuse me, you're using that, are you using that inequality?
I use this inequality.
Look at the one down there. There's an integral before that one.
Huh?
Down. This, look.
This one.
You're using the other upper. This one.
This, no, they are the same.
Yes, you're using this one down. So in terms of.
I use this one. They are the same. Huh?
Okay. Okay.
No, you can ask.
I'm wondering because this integral now is over y, for example.
This integral is over y.
What our is p now, LP.
And here I have x is Rn and y is Rn.
Okay.
Here x is equal to y is equal to Rn. But all that I use is the norm of the integral because I want to compute the norm of this. But compute the norm of this is the same as to compute the norm of this integral. But Minkowski says the norm of this integral is less than the integral of the norm if this term is finite. But if I compute now the integral of the norm, if I take this function is norm in LP, so I get the norm of what? Tau epsilon y minus f in LP. But since I take the norm, this does not depend on x, so this is a constant. So I bring out this term with absolute value. So I have phi of y. This inequality is true because Minkowski says for this inequality to be true, this term must be first finite. But look at if this term now is finite. Before I use this inequality, that I have to do is first I need to look at this term. But this term, since f is in LP, since f is in LP, so tau epsilon y, this function is where? Is in LP. Okay? This function also is in LP. But I integrate over y. Why this is finite? Phi is a function in L1. And this I can bound this term. Because this term is less than the norm of this plus the norm of this. But the norm of tau epsilon y is equal to the norm of f. So this term is less than 2 times norm of f in LP. So all that I have here is less than 2 times norm of f times absolute value of phi. But since phi is L1, so it means that this is an integral function. And so all this term is a finite term. Since this term is finite, now Minkowski inequality is 2. So this term is less than this. And this is exactly what we want to prove. This is exactly what we want to prove. And look at now, if you see, we start now to get approximation. Because if I have f a function in LP, and I take phi epsilon a modifier, from this estimation, if I let epsilon goes to 0, if I can go inside the integral, you will see that this term will go to, with some assumptions, this term will go to 0. And so it means that this term will go to 0. And so it means that f star phi epsilon converges to f in LP. And if I take phi to be smooth, for example, if I take phi such that this is a continuous function, so I have a LP function and I can approximate this LP function by a continuous function. Anytime I need a continuous function, if I take f, I take the convolution with phi epsilon. F star phi epsilon is a continuous function, and I know that f star phi epsilon also converges to f. And so I start to get approximation of LP function by continuous function. Okay. Tomorrow we will do these two results, C naught and D of omega are dense in NP by using this convolution. Okay.
Yep. You guys enjoy it, right?